medicine applications of machine learning, medicine and bioinformatics. Who knows machine learning here, or AI? Raise your hand if you've taken a course or if you have written code that does that. So most of you. The rest are, I'm assuming, interested but haven't had the chance to learn yet. These would be projects in urology, ophthalmology, radiology, oncology, neurology, and vascular surgery. I will start with urology. Do you know what that is? So one of the projects happening in this space is we're collaborating with a faculty member at ABMC to detect kidney stones during surgeries. So bahas, people get stones. Perhaps you're familiar with that. I hope you're not. And there's a lot of advancement now in robotic surgery. So some of the surgeries performed traditionally by physicians are now moving more and more towards, first of all, an integrated approach. So physicians are using robots themselves. And then in some cases, the goal is to have robots perform the surgery without the physician's intervention, or perhaps remotely come in. So these are things happening. And as part of that, different specialties need different things. In urology, what's needed is for the robot to be guided towards where the stone is. Whenever you're doing surgery, there are many complications. The body is moving as the patient is breathing or shifting, or they're laying there unconscious. So many things can happen. And when the body moves, things move with it. And if you're using a laser in order to burst something, you want to be careful where you hit that. You don't want to hit some sensitive area or burst a vessel or something. Because if it's made to destroy things like this, it can cause damage to more soft tissue, basically. So if we're trusting robots to do this, we need to be able to trust its guidance system. All right. So this is one of the projects in this space. And some students have worked on this. I have a video here to show you some results. So on the left, we're seeing the same footage basically. This is the stone, and this is the stone that's being highlighted by, we call it a UNet model. So this is every frame in this video is being extracted, a prediction is laid over it to show where the stone is, and then report it back. And this has been done offline. So we had these video recordings, and we managed to process the video and generate a new one. So we're not there yet, even though the results are pretty remarkable in terms of keeping up with the stone. We have so many examples. I chose this for clarity, but if you examine how the footage usually is, it's messy. Especially when this shatters, it can be in multiple places. This is clear, believe it or not. Most of the footage is blurry because of the different materials that are being thrown to by the machine that we're using, and because of the stone itself, and it becomes fragmented. So there are many difficulties when it comes to image clarity and detecting things like this. Another issue is speed. So, and you'll notice that some applications require live performance. For example, this one. If we're planning to apply this in surgery, we can't let the patient sleep overnight and then go home and run this algorithm so that we come back tomorrow and run this, right? We need to do it live. This requires a whole different set of tools and mindset in order to make sure it's running live, basically. Other applications are not as urgent, so they don't require as much sophistication perhaps when it comes to implementation. But yeah, this is one of the fields. There are so many different projects in this space. You're familiar with masks, I assume, from your social media apps. You know, you have a little Snapchat that started them, and now other tools, right? Things that are, they scan your face and then they mark some features and then lay things on top of them, right? So in surgery, there's interest in that as well. So imagine doing a surgery and having to overlay a set of, a patient walks in with an MRI image of some 3D scan of different organs. Physicians would like to see how the scans they have, because these are 3D models that they sometimes manipulate on their own machines. They might introduce some artifacts to plan their surgeries ahead. Rather than look at the screen while doing the work, they would like to see it kind of augmented with the physician's footage, with the patient's footage as well. So imagine having this footage, for example, that's for different organs, perhaps a kidney, a liver, something like that, and then watching an augmented reality version of that while performing surgery. So this is only one of the examples that are happening, and there is more. Stop me if you want to ask more about any of these. The whole point of this talk is to introduce examples, and if any spark interest or have any questions basically on your end to ask me so that we can talk more about it. Okay? Moving on to ophthalmology. And you know what that is? Alright, so we have a very active research group at ADMC, and so many different projects happening in that space. Some of you are already involved with a couple of those. This is what we're looking at here is what's called an OCT, an optical coherence tomography. So it's basically a scan, one of the scans that we can perform to the eye. And remember, so let me backtrack here. These projects that we're talking about here are at different stages of development, and particularly due to different stages of data that we have about them. So one thing you should know about machine learning is it is a data-driven solution. So the starting point is we usually have a data set, and so either we have a problem in mind that we'd like to solve, a question we'd like to answer, and we go out and collect the data that's needed in order to answer that. Or sometimes we do have data already that's available and recorded, and we wonder what can we do with that? What kind of questions can we answer? Alright? So here at the ABMC we have a lot of data, especially with Epic system being introduced, and it is one of the best hospitals in the region, and that's where many of these ideas come about. These are in different stages of development, and you'll see that as we go along. For ophthalmology, we have some data, I would say, but heavy interest in the field. So I will talk about a couple of projects related. One of them actually is to generate data. Who's familiar with GAN, or generative adversarial networks? Have you heard of those? Alright, so this is you're familiar with generative AI because I'm assuming you're familiar with ChatGPT. Right? But even though ChatGPT's application is in the text space mostly, this is by no means, when we talk about generative AI, it's not limited to text. And in fact, there's a lot of work in images. Right? And one of the projects we're working on is for fields and problems where data is limited. For example, when it comes to this, we have a couple of hundred scans, which are fine, but we need more for a certain problem. One of the projects we're working on is how to use machine learning to generate more synthetic data. And some of the results are remarkably. The work done, the way we do it is we build a system to generate synthetic data and then we needed to test it. So we send sets of images to physicians and ask them to vote whether it's a fake or a real image. And basically, we had 3 of these specialists, and their guesses were not better than random. So that's how the system was doing a really good job. If they couldn't figure it out, for the most part. Another project we're working on is, so using this, again, there's interest in guiding physicians' work during surgeries as well. So considering the basic or the other operations that are done to the eye, some physicians, especially the new ones entering the field, might have a problem. There are different segments. I'm not an expert when it comes to these, but I know there's an anterior and posterior segment, and they can be confusing to physicians during surgeries. So one of the applications we're working on is having kind of an assistant to surgeons to help them figure out things like which segment are we in right now. The eye is very sensitive, right? It's easy to mess things up if you're examining footage like the one we were looking at from neurology. In neurology, I think the zone is clear. Here's the zone, here's the that sort of thing. In eyes, it can be a bit confusing. Other things are helping. So in many eyes, they use lasers for many of the surgeries, and sometimes it's not immediately clear what the intensity used to be. So that's one of the things that we're working on, trying to predict using data that we have. For different types of eyes, different types of patients, different types of lasers, different types of machinery, can we help guide the physician to tune the settings for the instruments they're using to perform the surgery? That's another project. The one we're at the advanced stages in now is something related to a condition called keratoconus. Keratoconus is a disease of the cornea in which the cornea becomes thin and it has an elongated cone-like shape, which leads to loss of vision progressively and then in many cases total loss. And it's predominant in our region. So I'm interested in tackling issues and problems that are also popular or predominant in our region. This is one of them. And we have one of the largest data sets on this globally because of its popularity. Because this is common here, more common than other places, and ABMC is a good spot for this. We have some data on this. And so in this effort, we're seeing a lot of success in using machine learning to predict whether a patient has keratoconus or is developing keratoconus. Sometimes it's both eyes, sometimes it's only one of them. So there are different classes that we're trying to predict from, normal, and then keratoconus or keratoconus suspicious. So we're seeing good results using machine learning on a combination of, so really this is applied math and machine learning, because we're using something called Jernicke polynomials. Anyone familiar with those? So we're using some polynomials to try to match or fit the shape that we looked at earlier mathematically, and then using a machine learning system on these in order to make the predictions without getting into the details. This is again one of the projects in this space that's making it into production really. Dr. Sadi Awad has a system in this clinic, and we built the model, we deployed it locally, and then it's testing it on new patients and we're publishing the results. But this is actually quite promising. For the previous projects, Dr. Albert Haj is a urologist we're collaborating with, and he's also interested in deploying that, as I said, on one of the robots they use. So we're also in touch with the companies in order to, because here's where some complications might come in. When you have the best model, unless we're building the robot from scratch, you would need some company to offer you access to the interface so that you So far the data we've seen has mostly been visual, right? Whenever there's a lot of images because it's easiest to in the medical field to capture and to work with. And when it comes to radiology, things, some tasks are pretty simple. AI can really do really well given X-rays, find the fracture. Sometimes it does a better job than trained eyes, especially. And you know how images can see things we can't. Although sometimes it makes mistakes. Have you heard of the story where there were claims of artificial intelligence doing much better job than many physicians? I think it was detecting cancer, if I'm not mistaken. Turned out though one day, and this is one of the issues when it comes to applications in medicine and bioinformatics, a lot of interest is in explainability and accountability. That's why some people might wonder, that's doing well, why are we not seeing more and more? Legislation is a bit slower. Getting clearance and getting approvals in order to implement this is not as straightforward. Who can you blame if things go wrong? That's what we need as people. Who can you point the finger to? What is the system? We need someone. And so there is effort in trying to explain how these models are doing their work. Some are more successful than others. In this particular example I'm talking about, it turned out that when they examined how the model was, what it was looking on, the predictions, turned out it was focusing on so physicians write notes, and then they wipe them off in order to train the model on a clear state. Apparently they did not wipe it off completely, and to figure out basically patterns from what the note was kind of before and how long perhaps the word was before it was wiped off or something like that. And not the image itself, that's the point. The whole point was it wasn't examining the X-ray as much as how much was the segment that was erased before. So that was kind of a way up. But again, we're collaborating with the radiology department in order to one of the projects deals with X-rays for pediatrics and trying to find certain angles and certain measurements. This is simply a challenging project, it turns out. So you're looking for very small features in a much larger space. So this is one of the projects we've actually hit a block in, and we might continue perhaps when we have more data and clearer data. What else? Oncology, one of my fields that I'm interested in, and one of the things I'm trying to do, and this is one of the, this project I'm mentioning now is at the very early stages. It has to do with breast cancer, which we have. Breast cancer is more studied than other types of cancer, and we know more about its development, and so whenever there's something we can do something about, I feel like we're responsible to do that. And genetically speaking, there are certain mutations, there are certain biomarkers, that's what we call them, that we can look for to assess how much at risk someone is, right? And a famous example is celebrities do that. Angelina Jolie had the full mastectomy because she realized she's at high risk because of her genetic profiling, for example. And you can do that here at AMC, right? So we have the technology to screen and assess how at risk are you. The issue is, how do things like this work? And how does screening happen? You walk in, you get your genome sequence, perhaps not the entire genome, not the entire DNA, certain genes, and then these are matched against the database. For basically, there are tools that can analyze your specific mutations and tell you how risky, how much at risk you are of developing this. The issue with that is these tools are not built here. The data that they use were not populated in the region. They're not representative of you. Right? They're mostly tools from Western populations, and that's why they might work better for people there. Because there are certain, obviously there are genetic differences. Right? Not being racist. People look different in different parts of the world, and these are all reflected in their DNA. That's where it comes from. So these differences might have an effect on your health. Right? We're just saying how some diseases are more common in certain places than others. So we're at a disadvantage when it comes to that. And if we can do something about it, it might improve our prediction chances. And in this case, what you see as a physician is something called VUS, variants, which are mutations of uncertain significance. Why uncertain? Because we really don't know. We don't have a statistical significance to report. We haven't seen enough of this yet. So what I'm working on now is data collection and getting, so patients are walking in, so we need their approval in order to use that data, and that's the stage we're getting data at this point. And the methodology is ready. Once the data is, once we have enough of that, there are things we can do in order to make this work better for Lebanese and Arab women. In neurology, there's a lot of work related to neurology and mental health. I'll focus on neurology. So multiple sclerosis, there's a center we have here, and they have a good data set. We're working on trying to predict the most effective course of medication. It's a challenging condition. I don't know if you're familiar with it. Even diagnosing it isn't that straightforward. And it's one of the things where, if nothing else works, it's multiple sclerosis. But you try to rule things out, and that's how you get it. So we're trying to work on predicting optimal medication courses. Similarly with dementia. In dementia, we're actually working on a non-invasive approach. So the dementia, I don't know if you're familiar with it, or if you know someone who's developed it, usually it's in older populations. Instead of having them sit for an image, we're trying to do something that works on all these features. So one of the tasks is if a physician has a conversation with the patient. I was there with my grandma had hers, for example. And he starts, he was naming things. It was orange, tree, Honda, this. And then he talked and asked about my grandfather and, for 10 minutes, and then would ask again, what did I mention 10 minutes ago? So that's like a memory test, right? Things like this. And physicians use those in order to make certain diagnoses or refer to further testing. So we're trying to build something that works on these OD files, where someone can have or record the conversation and come up with some assessment. That's a bit difficult. There's also work in vascular surgery, particularly in something on predicting aneurysms and peripheral artery diseases. These kinds of projects usually, so in certain medical fields, they have what they call indices. They have certain rule-based methods. And if something is more than this many centimeters, they call it this level of tumor, for example, like cancer grades and things like that. But these numbers were determined sometimes due to actual careful experimentation. Other times, someone came up with them, but I don't know if it's been challenged since. So what we're trying to come up with is evaluate existing indices and perhaps propose new ones based on what we're observing from data that we are getting. Any questions so far? Alright. So this is a summary of some of the things going on with that involve applications of artificial intelligence in medicine, and particularly here at AUE. I will now move on to applications in genomics or bioinformatics in general. Okay. Who knows what this is? If you've taken my bioinformatics course, don't answer. Are you familiar? Nancy? Okay. Are you familiar with this animal? It's known for two things. One is the expensive coffee beans it generates. Right? So it's known to scramble for beans and then defecate them. And it's supposedly, since that's what it eats for a living, so it's supposed to be good at selecting good beans. So this is it's responsible for expensive coffee, as I will show you. The second thing is it's the primary suspect for giving us corona, right? COVID. I'm assuming you all know. My question to you is, how do we know that? And how do you, and this is again, and I invite you to think of this. You hear the news, and you were old enough when COVID hit to hear conversations about its origin. Perhaps some of the news are still circulating the halla. One day it was this country responsible for it, and next week it became another country. It was people changed their minds, and it's conflicting completely. They forget what they were saying the week before. Scientifically, though, how can we determine the origin of when it comes to epidemiology, the spread of disease? How can we figure that out? How can we determine it?
We talk about the sequence.
Right. So we sequence the genomes, and then how do we know basically
Similarity.
comparison, similarity? One of the tools actually used for this is called evolutionary trees. So we build trees in the technical sense, things like that look like this. And based on sequence similarity, we can do what we call, this problem is called clustering. What we're looking at is the result of the hierarchical clustering. If you're familiar with machine learning, then you know there are different types of clustering. If not, take my word for it. Right? What this tells me is the closest coronavirus to the one found in humans is from the palm pivot, which is what we were looking at earlier. And here we can try to see how this virus crossed the species barrier across different species before it made it to us humans. Alright? And this is, again, we're not going to give the full course on this, because it can be taken with a grain of salt. And perhaps some species were not sequenced yet, the bat is closer. But from the ones we've sequenced so far, this is the result or the conclusion we can draw. Not only that, if we sequence enough genomes from different people, at airports for example, we can figure out how it spread. Right? This particular example was for the COVID -19, but the same things apply. So we can figure out how it basically went across the globe.
I have a question. What do the numbers mean?
In this case, it was the score of similarity, I believe, in between the different viruses. That's a fair example.
هيدا لما كان القتال بالصين
كان القتال بالصين صح. So the numbers can represent different things depending on how you're comparing the sequences. It could be the similarity measure, it could be something else. So the starting point to this is, as you mentioned, a genome. Do you all know what a genome is? It's your code basically. Every organism has one. It's your DNA mostly. Some like COVID are RNA based, so not DNA. But let's assume it's a DNA sequence, which is the DNA is formed of 4 characters, A, C, T, and G, on repeat. Right? And a lot of the applications are now fueled by the starting point is genomic data, and this has been on the rise exponentially. I will talk about why. So what are some of the things that are happening in this space? We just looked at evolutionary tree construction. Sequence comparison doesn't have to be, it's less machine learning or rule-based methods. But once we have a genome, we'd like to predict what are the genes in it, for example. And then these genes code proteins. Proteins are the building blocks of life. And protein structure prediction is one of the famous applications of machine learning in this space. Kamal will talk a bit about it. Antimicrobial resistance is something I'm interested in. If you have an infection, you walk into the hospital, and then, I don't know, Kamal, this might ring the bell. Sometimes you take antibiotics, it doesn't work. Why? Because whatever you have is resistant to that medication. And we're getting more and more of these cases. It's becoming alarming. Actual estimates are by 2050, more than 10 million people will die a year because of this. That's no one's batting an eye. It's much worse than COVID. So that اللي ماتوا بكوفيد ما بيطلعوا على الأرض. So by scientific estimates, we're headed towards a catastrophe that's bringing us back to before penicillin was discovered. But I don't know what to say. I think we'll take it more seriously when more people start dropping that. Until then, we're fine. But machine learning is being used to, first of all, how do we figure out whether something is resistant or not? You walk into a hospital, they collect a sample of blood, and then literally feed petri dishes with different medications, and then they put them and wait. Let's see which medication works and which doesn't. And it takes sometimes up to a week. And sometimes people don't have that much time, especially if they are immunocompromised or after surgery. Again, you might have heard something like this is what they mean, right? And and again, it's getting really worse, especially homelessness. There are studies about AMR in Lebanon. طلع انه كل الشط بلبنان ما بعرف كيف ما بعرف عن جد هو كيف بعدهم عايشين بتروح على البحر يعني انه في different types of antibiotics, some more powerful than others, and the idea is I like talking about this. I'm going to take a minute. I'm not exactly machine learning related, but what we agreed on is let's hide some antibiotic so that bacteria doesn't get used to it. That's basically where our resistance develops. So we're like, okay, في هذا شيء اسمه colistin. حطه بالجارور, never use it. Are we all agreed? Okay, perfect. So we'll use all other medication and keep this one as a surprise. So whenever we encounter some strain, some bacteria that's resistant and is familiar with everything else, we'll sneak up with colistin and and then, but apparently, humans are greedy and but they always they have self-interests that are different. And across the shore in Lebanon, people call this the resistance. I have no idea where they're getting it from and how they're using it. And yeah, it's a bit alarming. Anyway, crediting violence factors, essential genes, all of these are important works in bioinformatics, especially in drug discovery. So a lot of work. The problem with antimicrobial resistance isn't just that bacteria are getting used to medication, it's that we're not coming up with as much medication as we used to earlier. Before كان يطلع يمكن تدري السنة، هلا واحد 12 سنين. The regulations are much stricter. Needs, I think on average every 10 years. And again, bacteria is working much faster than we are developing those drugs. So how can we use AI in order to speed up this drug discovery process? One is, given this bacterial sequence, see where it hurts. What's the essentials to that bacteria? What do we need to knock out in order to kill it? And then this is directly related also to protein structure prediction. Once we identify these essential genes, we identify how do they look like in 3D space. And then we get the protein structure, and then we learn, okay, if this is, think of it as a 3D puzzle really, where are sensitive spots in that structure itself? And then we come up with, either we find, we use existing medication that we see that is a good fit, or we sometimes come up with new compounds to synthesize in order to do that. Alright, so again, and the first genome project, it's called the Human Genome Project, took about at least 10 years to complete and cost about $3 billion. That's from 1990 to 2000. It's around the first genome. It's around 3 billion base pairs long, 3 billion characters. Now you can sequence your genome in over a weekend with a few $100s. Definitely less than 1,000. So you can see how this led to a significant rise in the number of genomes we have. There's a lot of interest in this. For COVID alone, a lot of genomes were sequenced for different species really. The goal is to have millions by the year 2030. We already have, I think, more than that for bacterial species. We have over 2 million human genomes, and these are used in order to find similarities and differences. By the way, this problem of genome sequencing, كمان هذه machine learning related, but I want you to know how much of it is computational. Right? So we talk about this in my bioinformatics course, so I'm taking the chance to spread it, just so you know how much the fields are, how much the computer science or engineering is applied in these natural sciences. And everything we're talking about, remember I just said the genome is at the center here. So for all of this to be possible, what do we need to be able to do? Sequence genomes. If it still cost us $3 billion, we wouldn't be having this conversation about any of this. How is it cheaper? It's because the machines that are being used now no longer try to sequence all the 3 billion base pairs. So no, what they do is they generate really short sequences, 100 base pairs, 100 characters short, and then they give it to us, the computational scientists, in order to put it together as a puzzle, as a really large puzzle. It's not straightforward, it's not the easiest, but we figured it out. So the solution to that is?
Eulerian path.
Right, so the solution to that is finding an Eulerian path and a De Bruijn graph. So it's graph theory, and it uses some mathematical tricks. If you're familiar with this, then you know what I'm talking about. If not, the solution is similar to the solution to this question. If we have these 4 landmarks with 7 bridges, is it possible to cross every bridge exactly once and end up where you started? So that's, the 2 problems are similar anyway.
How do you relate this problem?
We construct a graph, so this can be represented as a graph, right? Each of these landmarks is a node, and then the bridges are edges. And are you familiar with what a Eulerian cycle is?
Yes.
So if you find the Eulerian cycle, then it means it is possible to cross every bridge exactly once and end up, and you're using all the edges basically, but you're not using a node more than once. So similarly, we build a graph, a special type of graph, it's called a De Bruijn graph, out of these reads, and then the goal becomes, can we traverse all the edges? That's where the reads are stored, if you want. Exactly once, and then end up where you started. By that, is that you can find the starting place and then go over all the edges, all the regions exactly once. What you do is you're putting it together basically. Follow that path, and then you've used all of these and constructed the full, in case of humans, 3 billion base pair long genome. Yeah. It's quite efficient, it's quite, it works. Again, not machine learning based, but computational based, so I thought you should know. Proteins, though, when it comes to protein structure, so we know the shape of DNA, it's a double helix, right? It's been figured out, we know that. But when it comes to proteins, apparently their function depends on their shape. So they come in different shapes and sizes, and the shape determines what the protein does. Right? We can have an entire talk just about this, and it's quite interesting. But figuring out what the shape of a protein is not straightforward. So we have some experimental methods, but they're very costly, and we don't have time for that. And we have a lot of proteins. If you want to spend time scanning each of these, right? So we need, whenever we can use computational methods, we need that. But this is a very difficult problem to crack. The problem statement is simple. Given a DNA sequence, 1,000 characters long, can you predict or tell me what the shape in 3D of the protein that's generated by that is?
Just a sequence of letters.
Usually you have DNA, and then you know how proteins are made, right? DNA, RNA, and then amino acids. It's quite, it's limited. How many amino acids do we have? 20. 20. These are the standard amino acids. And then, so it should be quite simple. We couldn't 20, right? How much they can fold. Apparently in a lot of ways. And there's an entire institute working on that in Russia. The Russian Academy of Sciences has started working on this. It's been for decades, since the 1960s. And they couldn't, in my opinion, make any significant progress towards that for 50 years. And recently we've had a breakthrough in that. I'm not saying we've cracked the problem or we solved it. But I want to emphasize we've had a major breakthrough. Can someone guess what the, do you know, are you familiar with this? Have you heard the news? What company did this? Google, yeah. So a few years ago, it's called AlphaFold, DeepMind, and what I'm trying to say is the people who made the dent in this were people closer to you than. But you imagine working on this, a biologist in their white coats in their lab. So that's to show you that it might have been depressing in the other parts. We've been learning about proteins and structures and all this. You just had a garbage programming, and then they build a system to train on data and predict this. But yeah, it's quite remarkable, really. There's a lot of work still to be done here. So it's a breakthrough. It's not drug discovery grade yet. That's what I would say in a summary. So there's more to be done, and yeah, I think it's one of the most interesting problems to work on.
عندي سؤال.
تفضل.
لا كل شيء هو oriented للدراج discovery.
كل شيء وين بالحياة هنا؟
لا هون.
So when it comes to finding out the structure of proteins, a lot of interest is driven by drug discovery. Yes. And how does drug discovery work? Again, there's a ligand, a key and a lock, right? So you have this protein. One day I'll show you a demo. What we do is you move this around and you try to look for where can I fit something here. يعني إذا كلها sphere خلص عادي ما في يعني تعمل معه شيء. But sometimes you have some spots where you can insert something to disrupt its functionality, to prevent it from binding to something else, right, or activating something else. This is what you want to look for. But unless you know what it looks like, you cannot look for that. And you cannot run any of the computations basically to try to score how good it looks with something else. So this is definitely, drug discovery is one of the major interests in this, especially pharmaceutical companies. That's funding research in this space. But it's kind of our understanding. So as I said, the protein's functionality is determined by its shape. If you find examples, بتشوف إنه مبين شكله مثلا جراف، طلع تحوي أشياء ثانية, right? Things like this. So for us to understand and to unravel some of these mysteries of how an organism does what it does and how what exactly does it, we need to understand this. Knowing the shape, comparing it to other shapes, helps us understand what we're looking at. On the topic of uncovering unknowns, if you open a genome file, you can see a lot of these. So this is for some bacteria I downloaded. Usually every line represents a gene, and some information about the length, where it is in the genome, things like that, and hopefully an annotation describing what that gene does. And in this example, tRNA, MATCAT, it's doing something. Mobile element protein, insertion element. So these are things we know. Whenever you see something like this, you understand what this gene does. Right? Perhaps because of experimental studies, comparison to other things we know, مثلا structure. There's a lot of structure we can look for things that are similar. We assume خلاص بس هو على نفس الشيء. But a lot of the cases بيطلع عندنا شيء مثل hypothetical protein. What is this? This is predicted. يعني بنشوف okay, this looks like it's a protein, but we don't know what it does yet. And with all the advancements I was just telling you, there's a lot of blanks to fill. And we're not at the point where Allah we can go. There's a lot to be done here. And this is one of the things I'm interested in working on. One way to fill in these blanks and figure out what these hypothetical proteins are is find out if they are part of a group. Alright? So I know that Ahmed and Basil are part of a group. مثلا, and I know they're interested in AI. إذا حتى دارت معهم, I'm going to make the assumption إنه نقول هذه كمان هي interested in AI. That might not be true, but in many cases it will be. Right? So that's stereotyping working well. Exactly. So in genomes we have groups of genes that cluster together called operons. And predicting those and finding them helps us propagate these known labels to unknown ones. Alright? One of the successful examples is a group of 10 genes, 8 of which are related to photosynthesis. Most likely, and especially the larger the group is, the more we can make that assumption. Right? The rest should be close. So how do we usually do this? Scientists look at things like this, comparative genomic browsers, to try to see how much of an area is conserved, and then what the function of the different genes that are known are, and then try to propagate this again to different things. In one of my earlier approaches, I automated this process. So converted the genome into a series of these images, trying to capture the features that we need in order to predict operons, and found great success, but limited scalability. And dealing with images was a challenge. So in the more recent effort that Basil is involved with, what we're doing is building a large language model in order to do kind of the same task. So by using textual representations of genomic fragments, think of it, كيف I ask ChatGPT to help me with your homework and other things. So I'd like to ask it to help me find out where these operons are, where these clusters are in the genome, simply by describing what I'm looking at. Alright, so, and we have some preliminary results in that space, and we're still working on that. But the general idea behind this is building a foundation model. So literally, just like you have ChatGPT for journal tasks, something that is more targeted towards medicine and bioinformatics related tasks. So imagine the next time something like COVID hits, because it will. It's not something that was once this is something recurring. It wasn't the first time nor the second that it happened, and won't be the last. What we'd like is, given this new, whatever it is, virus or species, to sequence its genome, and then upload the file to some system, and ask it something like this. Here's a sequence, tell me the closest known relatives, what the essential genes are, and any known drug targets for these genes. And hopefully, and we won't have to wait long before we get answers. This is where I see the world heading now. This is how we're using the data we have. And this is, I would say, within our grasp. And we are getting there. I wouldn't be surprised if we see significant improvements in this. We have progress on each of these. One of the efforts is trying to put it together now. And let's upload this and ask a general question and see what we come up with. How to build a knowledge graph to organize all of this data that we're looking at. And that's all I have to share for today. If you have any questions or any comments, now is your